For section 10.6, we're looking at segment lengths in circles. We have a couple types of problems we're really looking at here. The first one is where we have segments of chords. This is where we have two chords that intersect inside the circle. It says if two chords intersect on the interior of the circle. We should note here it does not say that they're the center. That is where they meet. It does not say one of them is a diameter. It just doesn't say anything in particular about them. They just happen to meet inside the circle. And that's enough here. So if we have that, then the products of the segments of the segment lengths are equal. So if I look here, I have AB is one of my chords. I've said that EA times EB, and this is parts of AB, is equal to EC times ED, and those are the parts of CD. So I multiply the parts that are together, that make up the same chord, set them equal to the other parts multiplied together from the other chord. So I look at my first one here. 6 and 5 are multiplied together, and that's equal to 15 times x. That gives me 30 equals 15x, and x equals 2. So this value right here is 2. For my next one, I'm going to multiply now 12 times 5 equals 10 times x plus 1. That gives me 60 equals 10x plus 10, which is 50 equals 10x, where x equals 5. A couple more for us to look at. Here I'm going to do 4 times 3 equals 3x times x. That gives me 12 equals, now 3x times x is 3x squared, not 4x. If I was adding them, it would be 4x, but it's 3x squared. I divide both sides by 3, I get x squared equals 4. Take the square root, x equals the square root of 4. Now technically we could say plus or minus 2, but here we're only going to say positive 2, and there's a reason to that. Yes, in the context of just this problem where I solved it like this, plus or minus 2 would work, but the fact that I'm looking at lengths in a circle, I would not have a negative length value. They're always positive, so I have to take the positive solution. So x equals 2 is our answer. In algebra, though, if we had this problem we were solving, plus or minus 2 would be a correct answer. For our next one, I'm going to say x times x plus 4 equals x plus 2 times x plus 1. The left side, I get x squared plus 4x. On the right side, I'm multiplying binomials, so I'll use the box method. And that is x plus 2 times x plus 1. I get x squared, 2x, 1x, and 2. I combine my like terms, x squared plus 3x plus 2. So give me that. Now I'm simplifying. There's an x squared on both sides. So I subtract it from both sides. I get 4x equals 3x plus 2. Subtract the 3x, and x equals 2. If I wanted to plug the values back in, I would have 2, 6, 3, and 4. And if we look real quick there, 4 times 3 is 12, 6 times 2 is 12. They would work out. They'd still be equal. So that's when we have it on the inside. We're going to multiply the segments of the same chord together. Now if we shift to outside, here I'm going to have what we call a secant segment. And that's going to be, we know that a secant is a line that intersects the circle at 2 points. We're going to look at it in terms of a segment. So it's outside the circle, hits the circle at its 2 points, and that second one happens to be on the circle. So that is our secant segment. It's going to apply to the problems we look at next. Now that contains a chord of the circle, which is this part. And the other part is our next term, and that's the part of the secant segment outside the circle is called the external segment. And we're going to see why in a minute, why we need that. But realize every secant segment has the outside part and the part inside the circle. Lastly, we have the tangent segment, and we've talked about tangent already this chapter quite a bit, but we're going to use it again here, so we might as well mention it. The tangent segment has an endpoint on the circle and is perpendicular to the radius. So if I want to draw it off to the radius, it would go off there, but that would be our tangent segment. Okay, so we actually have two theorems here. The first one mainly deals with our secant segments. And it says if two secant segments share the same endpoint outside the circle, well, let's look real fast. They share E. They both intersect the circle at 2 points. Okay. Then the product of the lengths of one secant segment and its external segment equals the product of the lengths of the other secant segment and its external segment. Well, let's underline the important part right here. What that is saying is we're going to do the secant segment times the external. Now, like we just talked about on the last slide, the secant segment is the whole segment. The external is the outside part. So here I'm going to do the product. I'm going to multiply the secant segment times the outside part, which if we look here, EB, secant segment, EA, outside part. And that's going to be equal to the same thing on the other side, the secant segment times the external, or ED, entire secant segment, times EC, the outside. But that's the product we need to be looking for, and it's going to be on both sides. And we're going to have it in problems where we have two secant segments, like the example we have on the right. So if I look at the top line, the top secant, here I have the entire length, the total secant is 8, because it's 5 plus 3, times the outside, which is 5, is equal to the entire length here is x plus 4, because I add the two together, times the outside, which is 4. That gives me 40 equals 4x plus 16, becomes 4x equals 24, and eventually we get x equals 6. Okay, that's going to be the process as we go through for our secant segments. So well, I guess we're going to go to segments, secants, and tangents first, then we'll put some examples all together. Now, this is where I still have a secant, but I also throw in a tangent as well. So, if a secant segment and a tangent segment share an endpoint outside the circle, we have that. Then the product of the lengths of the secant segment and its external segment, so that stayed the same. So secant times external equals the square of the length of the tangent. Okay, well, why do we square the tangent? First of all, I don't have a part of the tangent that's not outside the circle. It's all outside the circle because it intersects the circle at one point. So I'm going to square this value, EA, set that equal to ED, the whole thing, times the outside part. That's going to be our rule for it's a tangent and a secant. If it's two secants, it's like the one we just talked about. But in this case, that's the process we're going to follow. So we look at our example. Tangent's 12, so 12 squared equals, I need the entire length, the whole secant, which is 3x plus 9, because I just added 1 and 8, times the external, which is 8. Gives me 144 equals 24x plus 72. Subtract 72, and I happen to get 72 equals 24x, and x is 3. So let's put them all together and start to identify them as we go through and solve them. So, first one, this is two secants. Two secants, we do the secant times the external. So, the entire length is 15 times the outside, which is 6, is equal to the entire length, x plus 5, times the outside, which is 5. I get 90 equals 5x plus 25. 65 equals 5x, and x becomes 13. next one. Now this is where I have them on the inside. When they're on the inside, I multiply the parts of the same chord. That'll be 3x equals 4 times 6. 3x equals 24. X equals 8. Down here, I have a tangent and a secant. I only have one value to that, so that's kind of maybe a hint that we have a tangent. There's nothing inside the circle. So the tangent squared equals the total length, 4, times the outside 1. Then becomes x squared equals 4. I then take the square root of both sides. I get the square root of 4. We're not going to say plus or minus 2. We're only going to take the positive because we wouldn't have a negative 2 for the length. So positive 2 is our answer. Now our last one here, tangent again. It's going to be 7 squared equals the total length, x plus 5, times the outside. 49 equals 5x plus 25. 24 equals 5x. I divide by 5 and I get 24 over 5, which is about, or it is actually 4.8.